Good afternoon, everyone. Here I'm glad to share this topic about the new shared memory mechanism design. Here is my agenda. Start from the brief review of memory model basis and then share the memory system design and the brief demo, then discussion of the application scenarios. First of all, let's have a brief review of the memory model. In short, the memory model is a set of rules about for memory users about how to use memory. Generally, there are two kinds of memory users. One is hardware and another is the software. Hardware users are usually the processing elements, such as general-purpose processors, accelerators, and ASICs, etc. General hardware users could any kinds of computing units that could issue memory access. From hardware's point of view, they would particularly consider the memory hierarchy and the memory attributes. Also, the memory order and atomic semantics abilities are also interested. From software designers' point of view, the memory model is mainly about the memory ability that being presented to programmers. So software designers cares about the points like how does the memory being organized in flat or sparse mode. Does the virtual memory architecture is enabled in a segment mode or the paging mode, and moreover, does the memory model support different access ordering and different atomic semantics to support software mechanisms like the different locks and or the lockless software abilities. Consider the multiple users of a memory system. We actually extend the single user memory model to shared memory model. As a software designer, the particularly cares about the memory model is something tricky on the cacheable or bufferable points of the memory system. Software mechanism need to some special efforts to take care of these hardware abilities to make sure the software can be running in a predictable behavior. Sorry. Sorry, my slide is a little out of date, so I'll jump to correct page. Here, we just take the memory pool as an example. We would discuss some aspects of the memory pool on this memory model basis, such as does the memory pool support the caching or the buffering? Does the memory pool support which kind of data caching, and how many operations could be buffered at a different place? And if the caching is enabled, will the cache coherence being implemented by hardware or by software? It's all about memory pool needed to care about. And some advanced points like the atomic ability and the data consistency assurance and access orders for the memory pool. It's a big problem for memory pool software. And before we jump into the software shared memory software for memory pool, I'll just review some existing shared memory mechanisms in Linux system. The first one is the System 5 shared memory design. Each shared memory region in the System 5 shared memory system is represented by a unique key. The user process could use the shared memory attached to map the shared memory region into their address space based on the unique key. And after attach, the user could gain the access control to the shared region if the user has proper access privileges. And if the user has finished the data consumed, it will have to call share memory detach and share memory control since library interfaces to control the shared resource. In a real user application, if the application needed to use the shared memory region to exchange data between its tasks, there are two additional important mechanisms is also needed. One is the communication channel that distribute this case for the memory segment to tasks. And the second one is the synchronization mechanism for the real workload to force the sequence of the use case for the shared resource. These two mechanisms is not contained natively in shared memory system. And a second mechanism I want to review it here is the memory file descriptor design in Linux. As its name indicated, each shared memory region in memory FD has a memory file as a backend in the memory, but the memory file has no file system entry, just anonymous file in memory, so there's no content on the persistent storage. The shared region is represented by a file descriptor. This enabled file descriptor-based operations like read, write, and map, etc. And one notable feature of the memfd is the sealing and unsealing state of a memory file. Once the file is sealed, the corresponding memory region is in a state like it cannot be accessed in some certain cases. It will just be accessed after the unseal. And there's some just like the System 5 shared memory, the memory file descriptor-based shared memory is not system-wide to all user process. It's just the nature of the just the nature of the file descriptor. It's kind of a per process resource, so it has more security benefits compared to system file shared memory. And on the two aspects I just mentioned in the communication channel for distributed file descriptors and synchronized mechanisms for different users of the memory file descriptor, the MFD and the system file shared memory was on the same line. They just both lack of such kind of ability. So next, I'll present our design shared memory system for memory pool. First, we introduced a kernel module, just the MP-SHAM kernel module to provide the interface for libraries. It provides the I/O control interface for users. Issue the share memory create or delete option to create and remove the region accordingly. And one notable option at the creation of a shared memory region in our design is the global share memory cache coherence option. That means if this option is specified at the creation time of the shared region, all users subsequently of all subsequent users of this shared memory region must in the same cache coherence domain. In short, the cache coherence domain it means all users will have a local copy or local cache for the shared data. But these local copies can be maintained by the hardware or by the software to keep these copies in a consistent way that for the memory pool shared memory system. This option means for MP-SHAM mechanisms, it won't care about the coherence abilities, just offload the responsibility to some other module. And once let's consider some use scenarios like the shared memory region is reside in the memory pool. The different users, such as different architecture systems like ARM system or some RISC-V system, will share data from the memory pool. So if the different, as I just said, different computing systems almost define its own memory model, and clearly the different architecture will have different memory models. So the single system memory, shared memory mechanism like MFD or the system file shared memory won't suitable for this scenario. So if that's why we have this new memory pool shared memory system, and we provide two important options at here. The first one is the DMC command, which stands for data cache maintenance, and another one is the GK option. GK option stands for the gatekeep. The data cache maintenance option means the MP-SHAM will take care of the cache and the cache coherence abilities, and the GK option means that it's similar to the seal and unseal option of the MMFD design. It just means after the GK, which stands for git keep, the users of the data will give up the access rights to the shared region. Let's take an example. The code blocks on this page simply abstract a use scenario of an application. It starts from MP sham attached to some shared region. Then in the worker function, it will produce or consume data within the shared region. After the work done, call MP sham detach interface to give up the access rights. It will do this cyclically in a loop. And just as the comments in the pseudocode, there are two data maintenance and git keep sub-functions was invoked on behalf of the MP sham detach function. Okay. Just one slide. Actually, this is a high-level abstraction of the working load for the user scenario of our shared memory system. And next, with on this page, we can see that the interface design of our system is not compatible with the existing applications. So, for a memory pool scenario, there's a certain existing workloads such as the large-scale database systems and big data applications, and some cloud applications, which would potentially have benefits from the memory pool scenario, could be worth to be modified to adjust the MP sham abilities to maybe these applications can be benefits from the memory pool. It also worth to add the native support into operating systems shared memory mechanism to natively enable the OpenOLA to be ready for these memory pool systems. That's all my sharing today. Thanks for listening.